Hi everyone and welcome to the video on rational functions. In this video I'm going to look at how to sketch these things both with and without a calculator and find all the important information about these kinds of equations. So a rational function is one that has basically been expressed as a fraction. So something that's rational can be expressed as a fraction, and so we can get these algebraic fractions. There's basically three groups that they fall into. So the first group is ones that can be simplified very easily, where you're just dividing by a single term. The second type is where you might need to use long division, something like that, in order to simplify. And then the third is where we can't really simplify very easily at all, and we need to use some fairly sophisticated algebraic techniques to deal with them. So I'm going to do this first one here. F of x equals x cubed plus 8 all over x. The first thing I notice here is that I am just dividing by a single term, and so I can very quickly and easily say, well, that's actually just going to be x squared plus 8 on x. And I will tell you right away that we could do this visually. So using addition of ordinates, that would be a pretty reasonable way to do this. I might even do that to begin with, just so we can get an idea of what the graph looks like. However, I will say that we are kind of expected to use a bit more accuracy in specialist maths, so we should be finding the stationary points and those kinds of things. So if I just do a quick sketch of what these actually look like, if I sketch each one out individually, the graph of x squared is just a parabola passing through the origin, like that. Notice I'm being really lazy with my sketch. This is just a rough one to give us an idea of what we're looking at. 8 on x is a hyperbola. The 8 is dilation from the... Interesting. The 8 is just a dilation from the x-axis by a factor of 8, so it's just going to make the graph go something like that. And the thing is, the scale doesn't really matter too much here. But if we use addition of ordinates now, then I'll switch over to a different color so we can see. The graph for the hyperbola part of it has an asymptote along the y-axis, so that's going to continue to be an asymptote. If we look at this particular x value, for example, we have a small positive value for the x squared part and a large negative value, so adding those together is going to be just a little bit above the large negative value. If we look at this, go about here somewhere, this value and this value here are about the same distance either side of the x-axis, and so they, when added together, would cancel each other out. It will pass through there. And then here we've got a small negative value with a very large positive value, and so that's going to give us a point up here somewhere. So this region of the graph is going to go something like this. The other side of it, if I look at this particular x-coordinate here, I can see that both graphs have the same point, and so when I add it, I'm adding a number to itself, so it just doubles in height. If I go a bit further out, I've got a small y value with a large y value, means it'll be a little bit above that y value. And same thing here, I've got a small y value and a large, so just a bit above. This section of the graph is going to look something like this. So that's what our graph is going to look like very roughly. Okay, we have that idea of it now. So the next thing is to actually figure out where our stationary points are, where our point of inflection is, and so on. So to get the stationary points, I'm going to do f dash x. And I'm going to use this form of the equation right here because it's going to be easier, although I might first rewrite it as x squared plus 8x to the negative 1 just to make it that bit easier. So when I differentiate that, I'm going to get 2x minus 8x to the negative 2, which could be rewritten as 2x minus 8 on x squared. And for stationary points, let f dash x equals 0. So that means 0 equals 2x minus 8 on x squared. I'm going to multiply everything by x squared just to get rid of the fraction. So 0 equals 2x cubed minus 8. Then adding 8 to both sides gives us 8 equals 2x cubed. Dividing by 2 gives us 4 equals x cubed. And then taking the cube root, we get x equals the cube root of 4. So there's our x coordinate, and we only have one x coordinate, so there's only one stationary point, which we can kind of see on our graph. It's that local minimum right there. So I will say that's a local min at x equals the cube root of 4. We could get the y coordinate for that as well. However, it's certainly not going to be anything nice. So yeah, let's just see how we go. That gives us x coordinate cube root of 4. The y coordinate is going to be cube root of 4 squared. Just because that's the x squared part. And then plus 8 over the cube root of 4. There isn't really a nicer way to express that, so that's our coordinates. The next thing is point of inflection. So we can figure out our second derivative. And in this case, it's going to be 2 plus 16x to the negative 3. So we can also use that to tell us the nature of our stationary point. 2 plus 16 on x cubed. So just to confirm that it is a minimum turning point that we found, we can go when x equals the cube root of 4, that's going to give us f dash dash cube root of 4 equaling 2 plus 16 over cube root of 4 cubed. Cube root and cube cancel out, so that just leaves us with 2 plus 16 on 4, which is 4. Anyway, that answer is 6, which is a positive number, and because it's the second derivative, what we're talking about is positive concavity, which therefore means it is a minimum. So we were right based on our picture. However, for point of inflection, let f dash dash x equal 0. So that means 0 equals 2 plus 16 on x cubed. That means 16 on x cubed equals negative 2. Or we could say that x cubed equals negative 8. And so x actually equals negative 2. And our y coordinate for that, if we substitute that into our original equation, f of negative 2 is going to be, just going to go back to it, well, it's going to be 0. I'll leave that other question there for after. So that gives our point of inflection at negative 2, 0. Which we can again see on our graph. It's pretty reasonable to expect that that might be our point of inflection. And what else do we have? The other thing, we've got a vertical asymptote, which we can see is when x equals 0, and that's because the denominator here cannot equal 0. However, there might be some other asymptotes. And this is very much a specialist maths thing. So the thing is that you can have, I guess you would say diagonal asymptotes, so still linear but diagonal, or otherwise you can actually also have non-linear asymptotes. So the thing is, I'll just do this off on the side here, I'll just call them other asymptotes. What we have to do is consider the limit as x approaches either positive or negative infinity of our original function. So in this, we kind of, I'd say that using long division is your best bet, or just, simplifying in the first place. So the limit, let's do the limit as x approaches positive infinity first, I'm going to use the simplified form, so of x squared plus 8 on x. I'm just thinking I want to do this a little bit differently. So the thing is that we can do this, the limit is going to be infinity, but the thing is what we're kind of looking at is what happens to each of these two terms here. So the x squared, like if we sub in a really large number going towards infinity, that's going to go towards like infinity squared, or it's going to approach infinity even faster. But the other term, the 8 on x, well, if you take 8 and you divide it by a really large number, like I'm talking stupidly large, then what it does is it basically becomes nothing. So what I could say is that as x approaches infinity, the 8 on x part of this equation approaches 0. And so therefore the function f of x approaches the other part, which is just x squared. So, and we can actually see that, looking at our original graph up here, each time, so I've got the x squared graph here, and as I move further out to the right, I'm adding on a smaller and smaller value each time. So by the time I'm getting out to really massive numbers, I'm going to be adding on virtually nothing. So it's going to be the x squared plus that tiniest little bit. And so in this case, the f of x equals x squared is actually behaving as an asymptote. And likewise, if we go towards negative infinity, so as x approaches negative infinity, well, the negative infinity, when we square it, becomes positive. So, it's still going to go towards infinity, but the 8 over negative infinity is going to make, again, basically 0, but it's going to be a negative value. And so I'll say that the 8 on x approaches 0, but it's actually approaching it like as a negative, so it's approaching it from below. And so we can then say that f of x is going to approach x squared. And again, we can see that perhaps from our original graph, the x squared is going to continue up there, getting steeper and steeper, and this is going to keep getting closer and closer as we continue out further. But it will just never quite reach it. It'll always be just that little bit below the graph of x squared. So we've just confirmed that the x squared is actually behaving as an asymptote in this particular graph, and so we can draw it as an asymptote. Helps if I go through the origin. Now, as with all things, we do label our asymptote. So we've got y equals x squared, we've got x equals 0, we've got our point of inflection, which was -2, 0, and we've also got our minimum turning point, which was cube root of 4 and all that. I'm not going to worry about writing that mess in. So that is what our graph looks like. I'm going to leave that video there and pick it up in the next one. So see you there.